Well then, guys, we need to achieve quite a lot today. And let's quickly finish with definite integrals. Do you remember what they are? It is simply the summation of areas under the curve. The areas could sometimes be negative if the curve is dipping below the x-axis. Good? So understanding what they are, let's see if we can very quickly evaluate the integral from 0 to 1, root of 1 minus x squared dx. Very quickly. Now, let me show you why that's very quickly. I look at the curve. What is y equal to root of 1 minus x squared for a? Y, you just said y equal to root of 1 minus x squared. And then look at it. You recognize that this is a very familiar formula. Do you agree? Very familiar formula, because when I square it, it's y squared equal to 1 minus x squared, or x squared plus y squared equal to 1. That is what? Remind me, what's x squared plus y squared equal to 1? It is a what curve? Name it. Exactly, Leaky. It is a circle of radius 1. You understand? So I look at this expression, I see the integral is from 0 to 1. If the integral is from 0 to 1, the shape that I'm tracing is that of quarter circle. Are you with me? Which means this is 1/4 times the area of unit circle, or 1/4 pi multiplied by 1 squared. It's 1/4 pi. I don't need to do anything. I can use geometry to figure out that area. Are you clear? Confirm, guys, if you understood the explanation. And mute your mics in case you're just joining. Good? Please faster. Kirill, yes. What about the rest of you? Do you understand what happened here? Nothing more than just setting y equal to and recognizing that I don't need to use this technique of calculating area. I don't need to approximate it by rectangles like this, because I already have other ways of obtaining that value. Now here is b. How do I solve integral from 0 to 3 of x minus 1 dx very quickly? This is a line. And if it's a line, it's always a sort of rectangle plus a triangle, where rectangle could be negative or positive or 0, and the same, well, it goes, similar thing goes for the triangle, okay? So b is very simple. B I can break into two formulas, right? I can find the integral of y equals x from 0 to 3, and the integral of minus 1 from 0 to 3. The area of the first is 3 times 3 by 2 divided by 2, so it's 9 over 2, and the area of the second is negative because y is equal to minus 1. So that would be minus 1 multiplied by the width, so it will be minus 3. So the answer is 9 over 2 minus 3, or 3/2. Do you understand, guys? If you are good with this, you can very quickly figure certain integrals without a lot of trouble. Now it's your turn. Do number C, please, and do it fast. Tell me what's the integral from minus 3 to 3 of root of 9 minus x squared plus x plus 2. Can you very quickly figure out what that area is? Or that integral is, to be more precise. Okay, Lisha, thank you. We shall see in a moment. You are correct, by the way, Lisha, yes. All right, guys, we should be ready. Here is the answer. One person did it. So what's the problem? You set y equal to root of 9 minus x squared, right? You simply have those shapes. We have a root of 9 minus x squared between minus 3 and 3. This is half a circle, upper part of the circle. Do you understand? Then we have x between minus 3 and 3. It cancels out because you have negative and positive area. So it cancels out to 0. And then 2 is just a horizontal bar over minus 3 to 3, which has area 2 multiplied by 6. So that's 12. So it is 9 pi over 2 plus 12. Do you follow? Confirm if you understood, or you need some more explanation. Good. One person understands. What about the rest of you? Are you even here, guys? You see, again, what are we trying to accomplish? We're trying to not just push symbols, but read the information and recognize what is it that we're doing. So how do we get 9 pi over 2? What is this? So root of 9 minus x squared, when I set it equal to y, that represents part of the circle. That circle has radius 3 and it's centered at the origin. Yes? Now, what's the area of a circle of radius 3? It's 9 times pi. But this is only the positive part of the circle. Y is positive, so that makes half a circle. That's why 9 pi over 2. Good? Okay, let's move on. Here is another example. Integral from 0 to 10 of f of x is equal to 17. Are you with me? So we don't know the function, but we know that the integral from 0 to 10 of f of x is 17, and the integral from 0 to 8 of f of x is 12. Find the integral from 8 to 10 of f of x dx. That's a simple question as well. So let's see if you can do that. Okay, Ping Ping, you're fast. Good. Very good. Very good. Okay, a few people see that. The answer is what, guys? What about the rest of you? Faster. The answer is 5. Why? Because the integral from 8 to 10 is the integral from 0 to 10 minus the integral from 0 to 8, which is 17 minus 12, which is 5. Good? So there are a few more things here. We might return to it, just calculating areas and volumes. Just a few of those pages, but let's move on to the next lecture notes to cover the essentials. So now let's talk about integration shortcuts, okay? So doing the Riemann sum is very, very difficult and tedious. There are other ways to go about it, and that's what we're talking about now. Good? So here is how we dealt with the problem up until now. We would take, let's say, a function like 3x squared, and what do we do with this function? We create, let's say, the right-hand method. We create lots of rectangles, take the limit as it goes to infinity, and we get our answer this way, right? Now, what's the link between this process and why do we use this symbol for indefinite integrals? It's the same as that for definite integrals. Why antiderivatives are represented as integral of 3x squared dx? Let's try to see what happens here. So I will explain the reasoning for that later. But here is a procedure that you may use if the function is continuous, okay? So if I want to integrate from 0 to 2 of 3x squared dx, all I have to do is find some antiderivative. Look at it. The indefinite integral of 3x squared dx is x cubed plus c. Good? So all I do is I take one such antiderivative, let's say x cubed, and evaluate it between 0 and 2. Okay? And what it means is that I plug in 2, so it's 2 cubed minus 0 cubed. You see that? And my answer is 8. Same answer I would have obtained if I carried the Riemann sum. Do you understand? So what actually ends up being the procedure, I will explain hopefully in a moment why that works, or try to explain why that works. For now, I want you to see if you can make that useful technique to figure out, let's say, what's the integral from minus 1 to 2 of x cubed minus 2x dx? What's that integral equal to? Do you understand that shortcut that I haven't yet explained why it works? But what you do is you find the antiderivative or antiderivative of this function and evaluate it at the top number minus evaluating it at the bottom number. So very simply, what's an antiderivative of x cubed minus 2x? Let's go to the solution. Look at it. X cubed minus 2x, its antiderivative is 1/4 x to the 4 minus x squared. Do you agree with me? And then what I do is I plug in 2 and subtract the result when I plug in minus 1. You see here plugging 2, it's 1/4 2 to the 4 minus 2 squared minus the same expression where I plug in minus 1. Are you with me? And simplifying, I get that the result is 3/4. Here is another example. Please evaluate B. So try to see if you can do it very fast. B, integral from 1 to 9 of root x. So that should take you 1 minute. All right, that's the answer. Okay, let's see what it is, guys. Very simply, for B, I take the integral of 1 to 9 of x to the 1/2. I need to find the antiderivative of x to the 1/2. Well, it's x to the 3/2 times 2/3. Do you agree? And then I plug in, that's this integral, right? Then I plug in 9 and I plug in 1. So the answer is 18 minus 2/3. Good? Do you understand what's happening, guys? The main point is, can you find the antiderivative fast? And can you see that you plug top number and then subtract, plugging in the bottom number? Now let's do C. What do you do for C? All right, C. One minute. All right, 1 minute is over. Okay, let's go about it. So see, all you do is you have 4 minus t times t to the 1/2. You distribute t to the 1/2, and then you take the antiderivative. You see, distributing t to the 1/2, we have 4 t to the 1/2. Antiderivative of that, it's t to the 3/2 multiplied by 8/3 minus, here it's t to the 5/2 times 2/5, and you plug in the value 4 minus this expression at the value 0, it's going to be 0. So it's really just plug in 4 and you have it. Good. Let's see if anybody answered it. Yes, we have some answers here. Good. Now, please calculate D. It should be even faster. You have 1 minute to figure out D. Okay, Lisha, good. If you finish with one problem, you right away go to the next one. That's how you save time. Very good, Irvin. If you're finished with this problem, go to E. Okay, good, Irvin. Move to the next question then. Okay, so let's do D, guys. How you should do it very fast, you understand? So this is not even a question. When I say 1 minute, that's way too much time for such problems, right? It's just a slack that I give you because it's your introduction. You should be able to do that in a few seconds. So we have the integral from 0 to pi over 4 of secant tangent. You have to recognize that secant tangent is the result when you take derivative of secant. So you just see that it's the same as secant evaluated from 0 to pi over 4. Good. So secant of pi over 4 is root 2, and secant of 0 is 1, so it's root 2 minus 1. Good. Now the next question is the integral of secant squared from 0 to pi over 4. So E, integral of secant squared. So you have 1 minute. Thank you, Lisha. E is very fast, guys. Quickly. All right, time is up, way up. So good, Erwin, you are moving you are moving onwards. So let's just finish E. The answer to E, what's the antiderivative of secant squared? You should know it to be tangent, right? I only see what 3-4 people participating. The antiderivative of secant squared is tangent. Evaluate from 0 to pi over 4. Tangent of pi over 4, you should know that immediately. That is 1. Slope is tangent is slope, so that's 1. Tangent of 0 is 0. So the answer is 1 for E. Now, very quickly, you do F. Blitzschnell. All right, I was wondering for a while here. What's the answer? The integral here of v cubed plus 3v to the 6 divided by v to the 4. The best thing we can do is divide everything by v. Simplify it. So when I divide by v to the 4, it's 1 over v plus 3v squared. And what's that? That's ln. Integral of 1 over v, it's ln of absolute value of v plus v cubed here. And then I evaluate it from 1 to 3. You see, guys? I plug in 2, so it will be ln of 2 plus 8 minus, when I plug here 1, I get ln of 1 is 0 and 1 cubed. So it would be ln of 2 plus 8 minus 1 or ln 2 plus 7. Yes? ln 2 plus 7. So confirm if you understand how that's supposed to work. Are you following, guys? Right? It's if you want to do it slower, you can go in office hours. That's possible. Good. Next is this question. Integral from 1 over root 3 to root 3 of 8, 1 plus x squared dx. Please solve it fast. Okay. Let's think of it, guys. What is this result? It's 8 over 1 plus x squared. What could be the function? What could be the antiderivative of it? So that's simply 8 multiplied by tangent inverse. You agree? Derivative of tangent inverse, you should know, is 1 over 1 plus x squared. So the result is 8 multiplied by this expression evaluated at root 3. It's pi over 3. Evaluated at 1 over root 3 is pi over 6. So the answer is 4 pi over 3. And I explain here with a triangle why. So pi over 3, we have root 3 over 2 is the opposite side, divided by 1/2 by the adjacent. So tangent of pi over 3 will give me root 3. Tangent of pi over 6 will give me 1 over root 3, which means those are my values here. Final question is this. Minus 2 to 2 of the function fx, and now the function is piecewise. It's equal to 2 if x is between minus 2 and 0, and 4 minus x squared if x is between 0 and 2. Oh, 2 messages, good. Are we ready, guys? The idea should be there in a split second, and the calculations follow a few seconds afterwards. What are we dealing with? We can break it into two integrals. Obviously, because the formula changes, we want to break it into the integral from -2 to 0 plus the integral from 0 to 2. Remember that I can break the function in between by any number. The number, by the way, where I break it in between does not have to be between -2 and 0. I could have used 7 as the point at which I break the function. But it's convenient to break it at 0. You follow? No? So 0 is in between -2 and 2. So the area between -2 and 0 plus the area between 0 and 2 is the area between -2 and 2. And if you are surprised, I'm not sure if I think I mentioned it in this class, or am I confused? I definitely spoke about it in the other class. Is that this number 0 could have been the number, I could have used 7 or 18 or any number. This process works. So anyhow, so that's the integral. First, it's the integral of 2, and second, it's the integral of 4 minus x squared. And when I simplify everything, I get, you see, the integral of 2 is simply from -2 to 0. I can say simply it's 2 times 2. It's like the line, the horizontal line from -2 to 0 of 2. So it's 4 plus the antiderivative of 4 minus x squared. It's 4x minus 1/3 x cubed evaluated from 0 to 2. And when I calculate it, I get 12 minus 8 over 3. Good. Now here is another example, guys. Let's see what would you say now. The integral is from -1 to 1 of 1 over x squared dx. What would be the value? What do you think is the value? Okay, Irvin says -2. Interesting. Come on, guys. So fast response. Khalil says -2. What about the rest of you? What do you say? Yes, so right, I want your signature in blood. If you think the answer is -2, type -2, please. Irvin, what, are you a psychology major? Say it's a trap. Yes, how well, you expect such bad things out of me, huh? Okay, but good. Okay, interesting. Very nice. Okay, let's look at this. Let's see the shortcut. Okay, so the indefinite integral of 1 over x squared, it's what? It's integral of x to the minus 2, which is minus x to the minus 1, yes? So then if I try to apply the shortcut, it will be minus x to the minus 1 from 1 to minus 1. And what is that? Then simply it is minus, I factor this minus out. It's minus 1 to the minus 1 minus minus 1 to the minus 1. So that is what? That's 1 plus 1 with a minus. So the answer is minus 2. Is it right? And as, of course, Irvin anticipated, it is wrong. Because thinking a little bit about it, can I get a negative number here? Well, maybe, I don't know. But you see, it looks like the area is positive. At 0, there is a discontinuity. Right? So you expect that it will be positive area. Okay? Now, that shortcut does not work in this particular situation. Why doesn't it work? Well, because, well, I mean, right now, of course, right now we haven't really understood what's the, you know, why the shortcut is working. So that's really our next goal. Why does the shortcut work and when does it fail to work? Let's try to get a grasp of that. Okay, so first problem to answer that question is this: given a continuous function, how do we find the average value of this function over the interval AB? Okay, so imagine that what you're doing is this. Okay, here is the illustration of what's happening. Imagine that you were a surveyor. You were, like from Kafka's book Ein Landvermesser, which is, I'm not sure if there is such a profession, but a measurer of the land. And your goal is to estimate, you see, you're walking on this mountain and you want to know how deep is this mountain over the bedrock. So you might have, like, let's say, a sand hill, and how deep is this over the bedrock? How would you go about to estimate how deep it is on average to the bedrock, to the x-axis? You understand the question? So in some places it's deeper, in some places it's not as deep. How do you estimate the average? So one suggestion would be this. Can you imagine? I mean, I usually, when I'm in class, I show it. So imagine what you do. You walk, you partition the x-axis into equal segments, and at the end of each segment, you push a pile driver into the ground, and you extract the length there this way, right? So you measure the length this way. You just drill until you hit bedrock, and you measure how far you have to drill. And you do that again and again and again for several values, right? So let's say that we will take n equidistant samples from the point A to the point B and average those samples. Are you with me, guys? Leiki, could you explain how the derivative of 1 over becomes well, because what's the antiderivative of x to the of 1 over x squared? So back to that problem for a second. Leiki, look at this. What is this function? This function is x to the minus 2. What is the antiderivative? What you do is you take x to the minus 2 plus 1 and you multiply by 1 over minus 2 plus 1. And what do you get? You get minus x to the power of minus 1. Yes? Yeah. All right, back to our surveyor problem. Right? Let's see how well you understand those ideas. Okay, guys? Are you with me? You follow? It's not too puzzling. Imagine that you have to create, maybe you're going to construct a building, or maybe that's an ore, and you have to know on average how far you must dig to the bedrock, to the x-axis here, right? And so how do you calculate the average? What you do is you take a bunch of samples, you drill in several places, take a bunch of samples, and you average those samples. Take finitely many samples and average them if you were a real life surveyor. Do you agree? You understand? Let's say you might imagine doing the same thing when you are when you're trying to estimate the depth of the ocean, right? How do you know where the ocean is deep? You might go into several places, maybe send a sonar wave and see how far it takes, how long it takes to bounce, and that's how you can estimate how deep is the ocean. So it's a similar idea here. I want to know what's the distance to the bedrock. So what will I get, guys? So how do I make the steps? I partition the interval from A to B into n equal segments. So I will take measurement at the right point of each segment. Does it make sense? So I will take measurement at the point x1, at the point x2, all the way to the point x sub n. And how do I displace to that point? I go a plus 1 times b minus a over n, right? A plus 1 times b over b minus a over n. That's the first place I take a sample. Are you with me? And x2 is 2. And then what is going to be the average of my altitudes? The average of the altitudes, it's 1 over n, summation k equal 1 to n, f of xk. You agree? I sum them because what do you do to average? You add up all the functions f and then you multiply by 1 over n. Good? Which takes this form. Which takes this form. You see this? 1 over n, k1 to n of f, a plus kb minus a over n. So far, so good? So it is reasonable, right? So because I took just finitely many samples, it's reasonable that if I push n to infinity, I become very obsessive and I take the samples at much narrower intervals, that I will get the average value to be the limit as n goes to infinity of 1 over n, f of a plus k b minus a over n, summation there. Guys, so please, before I move on, I mean, you're looking at this formula. Does the formula make sense to you? Do you understand why I take the limit? Right? If I take the limit, it's like I am taking denser points at which I average, and then I have a better sampling of the terrain. It's like, you see, I imagine taking the sample here, taking the sample here, taking the sample here, 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 and here, right? So those are the samples here. I add those up, and that will be an approximation of the average altitude. You agree? If I add them up and divide by the number of samples taken, that will be the average distance to the x-axis. And if I take more and more of them, it's reasonable to expect that, the intervals are smaller. It's reasonable to, as you can see, I'm tracing the curve better and better with more points, right? So it's reasonable to assume that I will get the actual average of this curve. That's how I define it. Yes? Now the function is very important. It's continuous function. You will see why it's important in a moment. So does this look familiar, guys? Look at it. I can push the 1 over n in here. So its limit as n goes to infinity, summation k1 to n, f of a plus kb minus a over n times 1 over n. Does this limit look familiar to you? What is that limit then? Look at it. You see, it looks like height times width, but the width is not quite right. You see, it's b minus a over n, and here is 1 over n. So what do you want to change? This thing. You want it to be b minus a over n. If you recognize that this is a Riemann sum, it looks like we are doing integration. I can just introduce here b minus a, and then I multiply by 1 over b minus a. Are you with me? Guys, are you still with me? Do you understand what I'm saying? I'm looking at the limit and I'm trying to come up with another expression for it. A lot of what we're doing, actually almost the entire class, that what we're doing is just, it's a problem of recognition. So it's not a difficult subject if you can recognize. Right? You just look at one mathematical object and recognize that it's yet another. You connect the two. So what is this limit? That limit is nothing more than the integral from f of x dx over ab multiplied by the length of the interval. Do you understand? Integrals are very similar to averages. That's a very deep insight. Integration and average are very simple, very similar things. Good? Let's see if you understand this idea. Okay? So without doing any calculations, determine this limit. So a, without any calculations, I push h to 0, 1 over h integral from 0 to h x squared plus 2 dx. I want you to tell me what will be the limit if I push h to 0. That's a test of your recognition. Ibad, beautiful. One person understands me. What about the rest of you? That limit is equal to what? All right, are we ready? One person got it. What about the rest of you? All right, then. Think about what's happening here. So first, without the limit, if h goes to 0, just forget the limit. I have 1 over h integral from 0 to h x squared plus 2. What am I doing here? And don't give me integral. You give me some very simple explanation. What is happening here? It should begin with the words I am surveying, or what, or something like that. Right? So what am I doing? I am surveying a landscape. That landscape is y equal to x squared plus 2. Yes? And between the position 0 and the position h, I am measuring the average elevation of that landscape. You understand? It's like a parabola opening upwards. At 0 it's 2, and then it goes upwards, and it's from 0 to h. You see why? Because we just calculated before here. I hope you understood this calculation. Is that if I see an integral of some function, and I see that I multiply that integral by 1 over the length of the interval of integration, then this is average. This is the average height. Do you understand? We calculated it before. Do you understand? So if I realize what I'm doing, I also realize x squared plus 2 is a continuous function, yes? It is a continuous function, which means that that the points, the elevations, when h is small, the elevations are going to be very similar to the elevation near the point 0, because they gradually change, right? So all the elevations are very similar to the elevation at 0. So the average will be 0 squared plus 2. Because the altitudes are all essentially the same if I push limit as h goes to 0, right? If h is very, very small, that's what h going to 0 means. If h is very, very small, then I'm averaging near 0. And if I'm averaging near 0, I will find that all the values are alike. All the altitudes are essentially 0 squared plus 2. Do you follow? Because the function is continuous. That's not true otherwise. The function is continuous, so let me give you a small drawing in case that helps. So look at it. This is what happens here. Let's say if h is positive, then let's say this is the point 2, and this is this curve. Now what happens if I select h smaller and smaller? Look at it. So if I select h very small, those elevations are very similar. If I select it even smaller, almost all the elevations are at 2. Right? Almost all the elevations in that region are at 2. So when I average, I will get numbers closer and closer to 2. Do you follow? Confirm if you do. That's an important idea that I will employ in a moment for the mean value, so for the fundamental theorem of calculus. Yes? That shortcut that you observed just a moment ago, you find antiderivative, you plug top number minus bottom number. That's conservation of energy. Definitely when you have potential and kinetic energy, for instance. They call it the work energy theorem. It's a version of the conservation energy theorem. In higher dimensions, it's the same. When you say no energy is lost or gained, when you say momentum isn't changed, what you're truly saying is fundamental theorem of calculus. You understand what I'm saying, guys? Fundamental theorem of calculus is the physical equivalent. In physics, it is conservation laws. So make sure, that's why it's called fundamental. Make sure you understand what I'm trying to tell you. Good? So let's see if let's see what people wrote. Okay, some people understand. That's nice. Not enough, I think. Others, I guess they shut off or something. They think it's the end of the semester. So, what about B? Look at it, sine x over x and 1 if x is 0. Please tell me what would be the average as h, what would be, sorry, as h goes to 0, 1 over h, integral from 0 to h, f of x dx. What would that be now? Yes, I'm waiting. So no need to do any calculations here. Yes. Okay. Lisha and Ibad, good. What about the rest of you? Yes, Reiki? Do you see what's happening here? I don't do calculations. Why? Because I recognize what the answer is without the need to calculate. I recognize what this thing is talking about. Good? So here, let's do B separately here. So if x is between 0 and h, sine x over x, if h is very small, is very similar to 1. Do you agree? So the values that we're averaging are essentially lots of numbers that are indistinguishable from 1. If h is very small, then I can achieve, let's say, up to 10 decimal points where it's 1. You understand? So the average is looking more and more like 1. So the limit will be the same as f of 0, or the value of the function at 1. The value of the function will 0 is equal to 1, I mean. So next question is this. C. Please, and notice guys, I changed something. I said from minus h to h, f of x dx. What is the limit when I push h to 0? 1 over h, integral from minus h to h, f of x dx, please. You see this? All right, what's taking a while? Oh, there are 4 people, 5. Okay. Oh, nice. 4 people say correctly. What about the rest? Good, Zakia. Good, Kirill. Beautiful. Beautiful. 10. The answer is obviously 10. Do you see why it's 10? Well, look at it. This would have been the average if I divided by the difference of those points. I should have divided by 2h, right? So what do? You see that this requires a 2h on the bottom to be the average. And the average would have been 5. You agree? Because tangent of 5x over x, if x is very close to 0, right, the average is approximately 5. So it's 5 times 2 or 10. You follow? Good, right? It's 10. Now, another example is, well, here is another example, guys. So now do the same thing. And be careful here for number D. Number D, what is the average there? What's the limit as h goes to 0 of 1 over h, integral of 0 to 3h f of x dx? Not the average, but what is this thing? Calculate the limit, please. Okay, Lisha says 0. Careful, think about it. So there is a value 0 when x is equal to 0, and then there is this thing, right? So first ask yourself, is this function continuous? Come on, guys, a little bit more. What can you say? Look at it. Ibad, a little. You're almost right. Look at it again. It's 3h in the integral, and it's 1 over h when we divide. There is no. It's one function. All right, let's do it together then. First of all, this almost looks like an average. Do you agree? It almost looks like an average, but it requires to have 3 to be an average on the bottom, because the size of the interval is 3h. So I need a 3 on the bottom. Yes? And if I put a 3, I multiply by 3. Now what we now have is 3, and then the average, the limit as h goes to 0 of the average from 0 to 3h. So there is, see, the function is piecewise. There is one value that's always equal to 0 in whenever we average, right? The function is equal to 0 at 0, right? So the function is not, the limit is not 0. The limit of as x goes to 0 is e squared, which is different from f of 0. But the average is 3 times e squared. Do you see why? Well, the result is 3 times e squared, because there are going to be lots of values, infinitely many values that are very similar to e squared when I take the average, and only one value that's 0. Do you follow? Look at it. Imagine that that you are one short person among giants, right? So you are Gulliver in the land of giants. There are a chameleon giants. They're all over 12 feet tall, and you are only regular size, right? So your size is not going to contribute much to the average. So 1 point will not contribute much to the average. There are infinitely many points in that interval that are like e squared. Do you follow? That's one reason. Look at the function. Look at it. That's going to be related to why we solve the integral improperly, right? So you use this shortcut, but that shortcut you will see works when the function is continuous. You see that 1 over x squared is not continuous at 0. Do you agree? 1 over x squared is not continuous at 0. So in some sense, at 0 there is going to be a sort of outlier, something that's not like the other values. All right, let's go and talk about the fundamental theorem of calculus. Are you ready? Take a deep breath. So here is the problem, guys, right? So are you ready? So for example, when I want to find the antiderivative of cosine x, well, I can say that the answer is cosine, well, the answer is sine x plus c. I can find a nice formula, right? But what about the antiderivative of cosine of x squared, or the antiderivative of e to the minus x squared? can I find a simple formula? Can I find an antiderivative for those functions at all? If you are going to try, you're going to struggle, and you're not going to find any nice simple antiderivative for those functions. Like for cosine, you guessed it's sine, but for e to the minus x squared, it will be difficult for you to guess an antiderivative for this function. In fact, if you do your ordinary guessings, you will never be successful. Yes? So here is we're going to define a new type of function. We define the function capital F of x. If you're given the curve y equals little f of x, you define capital F of x to be the integral from a to x of f of t dt. And I call it the slice of the cake function. And this is y. So suppose that your favorite aunt Jemima bakes your cake. And because you're in Calc 1, you don't deserve more than a one-dimensional cake. So it's going to be one-dimensional. And what you have then is this is the frying pan of the cake is from A to some other point, maybe to some other point B. And the point X is basically it's you are telling the aunt where to slice the cake. The cake is sliced at the lower point A, and it is also sliced at the point X where you specify. Because you are watching your weight, right? Once you specify X, this function will tell you how much cake you will be getting. You understand? The area of the cake you will be getting. Make sense? So this is the crust of the cake. This is the frying pan of the cake somewhere. And you cut the cake at point A and at point X. Are you with me still? And so that there is no confusion, I describe the curve as y equal to f of t. So let me here are some some questions regarding it's a comprehension check, right? So you have some cake. This is its crust, right? So if you tell Aunt Jemima x equal to a, what are you asking Aunt Jemima to do regarding the cake? Does the question make sense? Yes, Ibad. So do you understand this cake function, guys? I'm introducing a new type of function for you. Okay, and that function is once you're given, let's say the function, let's say given the function x squared, right? I can introduce the function capital F of x equal to, let's say, the integral from 0 to x t squared dt. And what does it mean? It means that you have this cake. Its crust is parabolic, and once you specify the point x, the cake is sliced at that point, and you obtain this region. If you say a different x, it will be sliced at a different point. Yes, that's our cake function. And the cake function just tells us, once I specify 2 points at which it's sliced, the default point it's sliced at point A, and the other point is at point X. Once I specify X, that piece of the cake is given to me, and its area is calculated so that I know how much cake I will be eating. How many calories will I consume is proportional to the area of the cake. So here is a comprehension check. In simple non-mathematical language, describe what you're telling your aunt when you specify that x equal to a. So here is the cake function from a to x, f of t dt, and you say, please x equal to a. What are you telling your aunt? Very good, Christian. You understand me. What about the rest of you? Exactly, Ibad. Now only two people understand this, guys. We're not speaking the same language. Are you with me? So x equal to a means you what? How much cake do you want? Okay, another two people are added. Okay, so how many do I have here? One. Okay, here we go. Good. So a few more people have added their names here. Good. It means that you don't want any cake because the area of your cake is 0, yes? Now, if you understand this, now tell me B. If I ask x equal to b, where b is less than a, what am I asking Aunt Jemima to do? We're assuming that the crust of the cake is positive. So for example, if I baked you a cake and you said x equal to b less than a, what should I do as a teacher and as a responsible, as responsible for your life? A little bit. What should I be doing? So now you're telling Aunt Jemima b less than a, please. Right? B less than a, please. What are you telling Aunt Jemima to do? That's goody, bud. Good. Exactly. So what it means, look at it. If b is less than a, guys, if b is less than a, then what do I have? I have, it's minus the integral from b to a f dt. It means you're telling Aunt Jemima to stick fingers in your mouth and make you vomit. You're bulimic. My God, you need help. Yes. Do you understand? Yes, good. So that's as simple as that. Okay. So now let's talk about this example, guys. Okay. So in this example, we are going to try to describe the precise relationship between the function f of x equal to x and capital F of x equal to the integral from 0 to x t dt. And we do that for several other examples here. Okay. Because we have little time, I will go ahead and talk about it myself. Good, but I hope you can follow me. So let's try to do this. Okay, I'm hoping that you actually are practicing Riemann integration, right? So what is f of x? It's the integral from in this case from 0 to x t dt, right? So what I can do is I can actually easily solve it because integral of 0 to x of t, geometrically speaking, let me just introduce the geometry here. Geometrically speaking, that means I'm integrating what shape? I'm finding area under what shape? I'm finding the area under what shape? Exactly, triangle. Good. I'm finding the area under the triangle. So right away, look at this thing and I say, oh, it's this triangle. So if this is to the point x, then the altitude will be x. So the answer is x squared over 2. This exact integral is x squared over 2. Are you with me? Do you understand that even without any calculation, I see that I can make this cake function very simple. It's x squared over 2. And what's the relationship? Look at it. X squared over 2. What's the relationship with x? Can you tell me, please? It is n. It is un or n. Antiderivative of x. It is an antiderivative. Derivative of x squared over 2 is x. So this cake function is a particular antiderivative, not a general one, but a particular antiderivative of x. You see? Written in the strange form, it's just an antiderivative of x. Very important realization here. Good? Next is, let's try to do the same thing with x squared. What's the relationship between x squared and the integral from 0 to x t squared dt? Now, I can use Riemann sums. Here I went through the Riemann sums. So I can integrate from 0 to x, and applying Riemann sums, here they are, right? That's the limit of Riemann sums. I get 1/3 x cubed. So again, I get an antiderivative of x squared. You see? So the relationship between in B is that this capital F is an antiderivative of x squared. Do you see that? So C, well, you have to be careful. I mean, you have to be, maybe so, Ibad, right? I just observed that this particular integral is a particular antiderivative, not a generic one, right? So now, again, we have 0 to x, and you are actually, in that case, you're right. 0 to x, I carry out Riemann sums. You see, here I went through the trouble of doing Riemann sums for you. I hope you remember how to do them. You know, you just divide the interval into n segments, you sum a bunch of things, and you have the limit. You understand? I did it by definition, and I observe again, the answer happens to be 1/4 x to the 4. So this function in C can also be expressed as something much simpler. This ugly looking thing is nothing more than 1/4 x to the 4. They are the same function. You understand? It's just another name for that function. It's an antiderivative of x to the 4. Are you following me? And if I do it for D, look at it, D. The integral is from 1 to x, 5t minus t squared. If I do that for D, what do you think I will get? I will get this expression. And when I take its derivative, I see 5x minus x squared. See? It's 4x minus 1 plus 3 over 2 x minus 1 squared minus 1/3 x minus 1 cubed. And if I take the derivative, I see it's 5x minus x squared. In other words, it's also an antiderivative. This is not a coincidence. Okay? I see an antiderivative everywhere I look. So here now is the fundamental theorem of calculus. Now look at it very carefully, guys. Let the function little f be continuous. Then for any a, the integral from a to x of f of t dt is an, not all the antiderivatives, it's an antiderivative of little f. In other words, this function, when I take its derivative, will be little f. You see, notice I switch the t here, but the integral from a to x, f of t dt, if when I take its derivative, I will get my little f function back. Okay? Now, how do we prove that to be the case? We just go to the definition. Okay? We go to the definition, and I will try to explain below what's the intuition. Why would somebody know that right away? Okay, why would somebody, it was, the purpose of this function is to be a clever antiderivative. So by definition, what is the derivative of capital F? X, it's the limit as h goes to 0 of f of x plus h minus f of x divided by h, which I can write as 1 over h f of x plus h minus f of x. Now, what is that? This is the integral of f of x plus h is the integral from a to x plus h minus the integral of a to x, right? And when I simplify those integrals, look at it, from a to x plus h, from a to x, what I have remaining is its limit as h goes to 0 of 1 over h integral from x to x plus h f of t dt. And that's nothing more. Look at it. The width of this interval is 1 over h. So that is the average function of f in the interval from x to x plus h, where h goes to 0. And because the function is continuous, f of t will be essentially f of x for all t between x and x plus h, right? If h is very small, the average will be the f at this point, at the x here. Are you following me, guys? I carry the definition and I recognize that it's the average value. So I need your some sort of confirmation that you understand this. I know maybe it looks abstract to you. I'll try to explain the intuition again in a moment. So I just proved that the derivative of capital F will be little f of x, provided little f of x is continuous. Where did I use continuity? It's in estimating the average. You see? So I obtain this limit. When I do definition of differentiation, I obtain this limit. Do you see how I obtain this limit? Simply, the derivative at x is x. Derivative at x is the difference at x plus h minus f of x divided by h. Now, this is the difference of integrals, so it ends up being the integral from x to x plus h times 1 over h. Now, look at it. This number minus this number is just h. So if I multiply by 1 over h, I'm talking about the average. So when I push h to 0, I hope you recognize from my explanation that's just the average of the function. Now, what's the average of the function from x to x plus h? That will be f of x in the limit, because if h is very small and the function is continuous, all the function values of this interval are very close to f of x, right? So the average will tend to, in the limit, it will tend to f of x. So that proves that the derivative is f of x as desired. Here, let me try to explain what was the intuition. Why did that work? Here is that original curve. Here it's zoomed in. Between x and x plus h, it's almost, the integral is almost that of a rectangle. So it's almost h multiplied by the altitude. That's another way of looking at it. 1 over h, integral from x to x plus h, f of t dt, is essentially 1 over h multiplied by the area of a rectangle that has height f of x and width h. You follow? In this integral, if h is very small, it's like I'm integrating under the curve from x to x plus h, and this area it can itself be approximated by one rectangle. Please confirm if you are with me, guys. That's very important here. You understand? So really the idea here was, how do you come with this idea, is because you realize that the derivative, it's just essentially a rectangle divided by its width. The area of a rectangle divided by its width will give you height. So then if you realize that, you can think that you can come up with this process, right? I hope once you see it, it's intuitive. That works only if the function is continuous, you see? So if h is small, then this strip is essentially a rectangle of height f of x and width h. And if I multiply it by 1 over h, I will essentially get f of x. Okay, so now let's try to see how that applies to the shortcut. Are you with me? Guys, are you with me? Here I'm trying to explain to you what's the shortcut. I really hope you feel excited, because you're realizing why you have no free will, for instance, right? Because to have free will, it means that you can change your momentum. But momentum is not changeable. So in theory, if I know the motion of all the particles in the universe at one moment, I know that for eternity in the future and eternity in the past, right? And I would use, to prove conservation of momentum, I would use the fundamental theorem of calculus. Yes. Can you imagine, right? So so pretty much now you understand why you cannot help but listen to me and I cannot help but talk to you, right? Or you are bored and sleepy and it doesn't matter, right? I just react in anger or whatnot. It's just a mechanical process. So let's calculate the integral from 0 to 3 of x squared dx. So here is how I'm going to do it, guys. Look at it. Instead of actually having this number, I am defining this function. Look at it. I'm defining f of x capital F of x to be the integral from 0 to x t squared dt. I make it into a function. You see, it's weird. I mean, it seems like I'm not only making things worse. It was a number, and now I make it into a function. I make it into the cake function, right? I realized that what happened here is that Aunt Jemima baked a cake with crust x squared, and then the person asked for the second slice to be at 3. The first slice was at 0, and the second slice was asked to be at the point 3. Good. So that is the integral from 0 to x t squared dt. Okay, in other words, I need to evaluate what is f of 3. By the fundamental theorem of calculus, I know something about this capital F. I know that if I take its derivative, I get x squared. Yes? So I know that this function is for sure 1/3 x cubed plus a constant. Do you understand? Because we know all the usual suspects, right? The only antiderivatives of x squared are 1/3 x cubed plus a constant, right? They all must be parallel. Do you remember that lecture, guys? So you see why I need the usual suspects. I know that the derivative is x squared everywhere at every point, which means the function itself has to be some sort of 1/3 x cubed plus a constant. But then I see what is that constant by plugging 0. If I plug 0, I get 1/3 0 cubed plus a constant. It's equal to the constant, and that must be equal to 0. Because look at it, at 0, if I set x equal to 0, it's the integral from 0 to 0. Do you follow me? So that means that my function capital F of x is simply 1/3 x cubed. So I was able to replace this integral, the definite integral, by 1/3 x cubed. And so what is f of 3? F of 3 is this function where I plug in the number 3. So the answer is 9. Now let's see if we can do that in general. In general, if little f is continuous and we can guess a simple antiderivative formula, then we know by the fundamental theorem of calculus that yes, we know that we have this area definition here, right? So we have capital F of A is the integral from a to x f of t dt. Now suppose I'm able to guess some antiderivative that's more convenient for me to use. Because by the fundamental theorem of calculus, the derivative of capital F sub A is also little f of x, then I know that the relationship between my guess and the actual formula, the actual function I must use, it's that my actual function is the one I guess plus a constant. So guys, I need your confirmation. Do you understand, or are you confused by this point? You understand what I do? I need to calculate area. Here is my goal. I need to calculate area from little a to little b of f of x dx. So what I do is I make it into a function, right? I say, okay, let me figure out what's the function from a to x f of t dt. Here is that function, you see? Let me do that maybe with a particular example so that you hopefully can follow, right? Suppose that I wanted to integrate from 0, or let's do it like this. Let's do it from pi over 4, okay? I wanted the integral from pi over 4 to pi over 2 of cosine x dx. I want to know this, right? It's not easy to do using Riemann sums. Do you agree? But cosine is a continuous function, and I know, and I do this, okay? So I define the function capital F of x to be the integral from pi over 4 to x of cosine t dt, okay? By the fundamental theorem of calculus, the derivative of this, let's call this sub a here, right? The derivative of this function is what? The derivative of this function is simply cosine of x. You understand? All I know about this function, capital F of A, you see from this function, I know that this integral is simply capital F sub A. Capital F sub A of pi over 2 is what I want to evaluate. Right? It's this function at pi over 2 that I want to evaluate, because this number should be pi over 2, not just some arbitrary x. Okay. So how I proceed is this. I take the derivative of my integral, and I see on my integral function, I see I have cosine x. And then I ask myself, but I know antiderivative of this function. What's the antiderivative of cosine? It's sine x plus c. Yes? Sine x plus c. So that because they're also the only possibilities, right? That's why it's important to know that there are no other exotic functions, right? So it must be sine x plus c. Those are the only functions that can produce cosine by differentiation. Do you follow that, guys? Do you understand why I know that? Because if the derivative are the same, it means that the curves that I'm tracing, are parallel. Remember, right? Because if the derivatives everywhere are the same, we have parallel lines. Yes? Creation, I should sing you a lullaby. It's a lullaby, and it's cosine. And so that means that capital F, I understand, I also want to sleep. I don't even want to wake up anymore. So what's this function? I'm trying to find this particular function. So what I know about it is that I know that my integral from pi over 4 to x of cosine t dt is equal to sine x plus c, but I need to know which specific c will I get. And the only nice value to plug in is plug in pi over 4, because integral from pi over 4 to pi over 4 is 0, right? So I see that sine of pi over 4 plus c is equal to 0. So that means c is equal to minus sine of pi over 4. You see what just happened here? I guess that sine is an antiderivative. So what happened here is that it means that the integral from pi over 4 to pi over 2, pi over 2 of cosine t dt, it's simply sine of pi over 2 minus sine of pi over 4, because that was my constant c, and this was my function capital F a of yeah. So basically, sorry, let me write it better this way. So because my integral function, my capital F a of x, happens to be sine of x minus sine of pi over 4. Are you with me? I just was able to find the actual function. You understand how I reason? I use my understanding, geometric understanding of the derivative, you might say, and I know that because I can guess a simpler formula for an antiderivative of cosine, right? I know all the possibilities for this function here. You see? So in general, what happens in general? In general, I can establish how to find the c so that I don't have to think of it all the time anew. So if I integrate from a to x, f of t dt, if I do that integral, then what do I get? I get that if I can guess an antiderivative is that this complicated integral function is equal to the simple antiderivative plus c. Now I plug in a and I get 0. So that would be the simple antiderivative at a plus c, and so c is equal to minus that simple antiderivative. So that means that the integral function is equal to the antiderivative I found minus that antiderivative evaluated at A. Okay, and that gives me this formula, right? So that gives me capital F of B minus capital F of A. Is that it's the same as F of X BA. Okay, do you see how that works? So by the way, there was a student once that the student did not learn much about integrals, but he understood the fundamental theorem of calculus. So there was a loophole, and because of that loophole, and I actually thought it's very clever, I gave the student all the questions for the integral test correct. Okay, so here, solve the integral A. Solve integral cosine x dx, please. Tell me what this thing is. So this is just asking for the antiderivative of cosine, right? So some people, and most people, what they would say this equals to sine x plus c, right? You know what one student did? He just said this. Okay, it's the integral from, let's say, 0 to x cosine t dt plus c, and that's correct because the derivative of this function happens to be cosine. The answer is correct. Okay, without any work. Do you understand? Now, similarly, what about b? The integral of e to the minus x squared dx. Sometimes you're able to find a nice formula, sometimes not, but there is an antiderivative, and that antiderivative can be written, let's say, as the integral from maybe 0 to x of e minus t squared dt plus a constant. Yeah, and I can do the same thing here. Here is a v. I can write this integral. I can use any value I like. Maybe I use 1 here. 1 to x tangent inverse of t plus 1 over t cubed plus c is the answer to c. Let me release my cat. He's screaming. You understand what I'm trying to say, guys? So those are the possible solutions. I can just place anything I like here. 1 to v tangent inverse t plus 1 over t cubed. 0 to u t cosine t of u, right? Good? You understand that what I'm hoping? I mean, I'm not sure. I imagine you forgot it before before I even finished explaining it. So bothers me very much. Okay, here is your next task, guys. Right? Let's finish those questions, and then we'll call it a day. Yes. So look. Okay. So take the derivative of the integral from 1 to x to the 4 secant t dt. What's the derivative here? And I want fast. Here I just received a message. As always, there are students that are not registered from my open math. Are you all registered from my open math? And people ask me like the same question redundantly. You're all registered, correct? Irvin, very good. So here is the answer to 1. So I plug, so the derivative is what? The derivative is you always plug in this value. So it's secant x to the 4, and then multiply by the derivative of that value. It's chain rule, so it's 4x cubed. Yes? The next example is from 1 to x, 1 over t cubed plus 1. What's b? Please do it very fast. B. You understand? So, so when you take derivatives of functions where you have some variable on the top, you just place this variable into the integrand and multiply by the derivative of that integrand. Now, what's b? Very good, Ibad. So for b, I simply write 1 over x cubed plus 1. Good? Very good. Now, what is it for c? Okay. Okay, good, good. So let's look at it. What do you want to do here? Before you carry any calculation, you want to write it as minus the integral pi pi to x of root 1 plus secant t dt. So when you take the derivative, it's simply going to be minus root 1 plus secant x. Clear? And you can do that once you get comfortable very fast. Now do please number D. Because x is on the bottom, x has to be on the top when you use the fundamental theorem of calculus. So to make x go to the top, I multiply by -1. Make sure that you understand the fundamental theorem of calculus and not just kind of symbol push. We studied it for a short time, but you have this video and you have this notes. You should look through them. Okay, Irvin, good. So the answer to D is what? There would be a negative because sign is on the bottom. So the answer should be what? Should be negative root of 1 plus sine squared x multiplied by derivative of sine, which is by cosine. Good. Now do number E, this one. Fast. That's good, Ibad. Very good. Okay, Irvin, good. Very simple, guys. What can you do? I think I mentioned that you can introduce a constant in between. It can be in between cosine and sine, but it can be anywhere. Any constant works. You can break the integral by a constant. So it's the derivative of the integral from cosine to the constant plus constant to sine. And when you take the derivative, the lower part becomes negative. This part becomes positive. So this is the general situation. If you have derivative from ax to bx of f, it's f evaluated at the top function times the derivative of top function minus f evaluated at bottom function times derivative of bottom function. That's clear when you just think about it a little bit. Good? So for example, in f, the derivative from x to x cubed of e to the minus t squared dt, it will be e instead of t, you plug x cubed times the derivative of x cubed minus e, you plug the bottom function times the derivative of the bottom function. Okay, and then I will leave you to think about this last problem. Okay, to see you have integral within an integral. And this is the last line here is explaining why you change parameters. So if you want to look at it, it's very interesting there. Why do we change parameters? Why don't we just write a to x f of x dx? Why do I change to a to x f of t dt? But I think you're falling asleep, and here is one thing that I want you to know. There is lecture 7, the substitution rule. Okay, make sure to go over that section before the final. I plan to do the following. I plan to do a review over the weekend. I will let you know more. And of course, Monday. All right, Monday is reading day. And I plan to invite you to continue with the review. Have you seen the review, guys? Have you started reviewing for the final? Do you realize that it's going to be deadly? Based on how I see how you process it, it's going to be very deadly final exam. It's going to be abstract as an anti-cheating method. So you should be doing my open math. There is a practice exam on my open math, and this exam is also posted on Brooklyn College website. I forwarded it to you before. I'm going to do that again, right? I'm going to send again a message. You see, Gabriel has a very good review, right? So I will say, I haven't seen it. So what's the review? Yes, Professor Suzuki is the one who created the final. I haven't seen the actual final. Could anybody tell me? I might look at the review myself. So is it the same exam or the review is another thing? There is like a simulated exam, right? Where you can practice posting the solutions, everything, right? Is it that same exam or is it generating a random? Yeah, of course. Good. You mean you mean you're watching his short videos on calculus? I will forward those to you if you need. All right, guys. So, okay. So I suppose, well, guys, have a good day. Maybe God Almighty will protect you on the day of the final.